All right, so we're going to talk about section 12.4, tangent vectors and normal vectors. So when we interpreted our position vector, we said we talked about our vector value function r of t. When we interpreted it as a position vector, we said that we decided that r prime was tangent to the curve represented by r of t at a particular value of t. So r prime of t is tangent to r of t at some time t. And we interpreted r prime as a velocity vector. So r prime is going to point in the direction of increasing parameter. So it's the direction that we're moving along the curve. So r prime points in the direction of an increasing parameter. We said it was a velocity vector. Well, we can extend this thinking and interpret r prime as a tangent vector and that points in the direction of increasing parameter of any vector valued function. We don't have to interpret it as a position and a velocity. We can just say that r prime, or r, is some vector valued function. R prime is a vector that's tangent to r at a particular time t, and r prime points in the direction of increasing parameters. So we don't necessarily have to think of it as position, velocity, and acceleration to extend that interpretation to any general vector valued function. So what we're interested in this section is we know that r prime is a tangent vector. We want to come up with a unit tangent vector, because as we go further with studying vector valued functions, this unit tangent vector is going to be useful. We're going to end up using it a lot, and then we're going to find a unit normal vector, and that's going to be useful as well. So we're going to use this interpretation of r prime being tangent to r and pointing in the direction of increasing parameter to define our unit tangent vector to a curve. So we're going to say our unit tangent vector, and we usually use a capital T. Is just going to be r prime over the length of r prime. Oops, then I want to put my functional dependence here. There we go. So that's how we define our unit tangent vector, and this is defined on any open interval where r prime is not 0. So we're saying the curve represented by r of t is smooth. And we use this a little bit. One of the problems we did yesterday, we kind of used this idea, the one over here that Eric and Andy worked on. So I want to do another example like that, just to kind of show how one way that we would use the unit tangent vector, calculate a unit tangent vector, and just make some use of it. And then we'll talk about our unit normal vector. So for our example, same kind of problem that we talked about yesterday. We have r of t, our vector valued function, is given by e to the minus t, 2 cosine t, and 2 sine t. So we want to find a set of parametric equations for the tangent line to the graph, at t0 equals 0. And then we want to use that to approximate our position at point 0.1, so 0.1. So this is exactly like we did back in Calculus 1, where we said we want to write the equation of the tangent line to the graph at a particular time. So because we're in 3 dimensions, we have to find a set of parametric equations for the tangent line. First off, what kind of curve is this vector value function going to represent? It's going to be a spiral. So this 2 cosine t and 2 sine t gives us a circular motion. So it's going to be going in a circle about which axis? About the x-axis. And what's this e to the minus t going to do to that spiraling motion?
It's going to look kind of like a black hole.
So Chris says kind of like a black hole, so it's going to spiral, and as it gets closer to the YZ plane, it's going to spiral faster and faster and faster and faster and faster. And in the limit, as t approaches infinity, what curve do we have?
Circle.
A circle in the YZ plane, right? So we have this kind of spiraling motion that gets faster and faster and faster. So that's what our curve looks like. So we want to find, and we're looking at the tangent line to the graph at t0 equals 0. So to write our set of parametric equations, what 2 pieces of information do we need? What is it?
R prime.
We need r prime of t. So thinking more basic, thinking just about parametric equations for a line. What pieces of information do we need to write the parametric equations for a line? The a, b, and c, the direction numbers. So we need the direction numbers or the direction vector. And we need one other piece of information, a point on the line. We need a direction vector and a point on the line. And Garrett said we need r prime of t. What's r prime of t going to give us? Our r prime is going to give us our direction vector, because r prime is tangent to the curve. So our direction vector comes from r prime of t. And how can we get a point on the line? Plug in 0 into r. So a point on the line is going to be r of t0, and I'll put the t0 here. The direction vector is going to be r prime at t0. So this gives us our point, this gives us our direction vector, and then we can write our parametric equations. So let's write r prime of t. So what's our R prime vector going to be? Minus e to the minus t. Minus 2 sine t. And 2 cosine t. So there's our R prime, and this is going to give us our direction vector. So R prime of t0, R prime of 0, we get -1, 0, 2. So our direction numbers are a equals -1, b equals 0, and c equals 2. And our point on the line, r of times 0, I get the point 1, 2, 0. So now we can write our parametric equations. Our parametric equations for the line are x equals 1 minus t, y equals 2, and z equals 2t. So there are my parametric equations for my line. And then we want to approximate r of 0.1. So we're using the line to approximate our position at time equals 0.1. So I just substitute in time equals 0.1 into my equations for my line. So r of 0.1 is going to be approximately 0.9 to 0.2. Does that process make sense? So that's one way we would use a tangent vector. We didn't use a unit tangent vector. We could have. The unit tangent vector would still give us direction numbers for the line. But we were fine just using r prime to find our tangent vector. All right, so we have a nice easy method for finding this unit tangent vector to our curve. We're also interested in a specific vector that's orthogonal to t. So now we want to analyze our curve, and we'll extend this as we go on. We want to find a specific vector orthogonal to our unit tangent vector. And to do that, we're going to go back to our properties of derivatives of vector value functions. If we remember, and I'm going to say recall, because I don't get to use that word very often. Recall that if r dot r equals a constant scalar, then this is one of our properties of derivatives of vector valued functions. We said that r dot r prime equals 0. So that was one of our properties, and I said when I listed that property that was going to be useful later on. Well, here's one of the times where it's useful. Now before we move on, why Anybody think why this would be the case? If r dot r is a constant, why would r dot r prime equal 0?
There's no t's in derivative of 0.
Okay, so Cole says there's no t's in the derivative. So let's,
There's no t in the regular function.
there's no t in the regular function. Well, there's,
Well, not necessarily.
but it has to do with the derivative. So you're on the right track. So let's do a quick proof. This goes really quickly. We're going to say r of t dot r of t equals 0. So I'm going to take the derivative of this. d dt of r of t dot r of t equals, the derivative of 0 is just 0. So we take the derivative of both sides. What's the derivative of r dot r? We're going to use our product rule, one of our product rules. So this is r of t, I'm going to drop the t's here, r dot r prime plus r prime dot r. And that equals 0. And r dot r prime plus r prime dot r is what? 2 is the order doesn't matter here, so this is 2 r dot r prime equals 0. So we know that r dot r prime has to equal 0.
And if it was any other constant, then it would still be sort of the derivative would still be 0. Not really so.
I could start out here with a constant here instead of 0, because the derivative of constant is 0. Yeah. So what the answer to your question is yes. I should have written that c there. So r dot r prime equals 0. If the dot product of those two is 0, what does that tell you about those two vectors? They're orthogonal. All right, so this gives us our tool to find a vector orthogonal to our unit tangent vector. We defined t, our unit tangent vector. T is a unit vector by definition. We defined it as a unit vector. So t dot t is going to be what? We define t to be a unit vector. So if we take the dot product of the unit vector with itself, what's it going to be? 1. T dot t is going to be 1. So using the little proof that we just did, so t dot t prime has to be 0. So then t prime is orthogonal to our unit tangent vector. And then what we do is we normalize t prime to get what we call our principal unit normal vector. Principal, yes. So our principal unit normal vector, and we use a capital N. N of t is t prime over the length of t prime. And this is defined where we don't want to divide by 0, where t prime does not equal 0, and R is smooth.
Like, a unit vector and then a unit, like, or you have a unit vector and then making another, making a unit vector again?
Well, T prime is
Oh, they're not.
T prime is not necessarily a unit vector. T is a unit vector, but T prime is not necessarily. So we have to make sure that our vector is we want the magnitude of our vector to be 1. Yes.
What's the practical application of this?
So let's think about the application of the unit normal vector. So think about it, we interpreted our vector value functions the other day as position vectors. We talked about velocity and acceleration. So our unit tangent vector is going to point in the direction of the velocity. In uniform circular motion, what vector is orthogonal to the velocity vector? The acceleration vector. The unit normal vector has to do with, if we're interpreting this as in terms of motion, the unit normal vector has to do with acceleration. So, and what we're going to do, we're not going to do it today, but what we'll do is we'll break down the acceleration as a component of acceleration tangent to our motion and a component of acceleration normal to our motion. The tangent component of acceleration is going to speed you up or slow you down along your direction of motion. The normal component of acceleration is what's going to change your direction. So that's kind of where we're going with this unit normal vector. So we're going to break down our acceleration into two components, and that gives us information about our curve. Couple of things about the unit normal vector. N points to the concave side of the curve. And the other way you could think of it is it points in the direction that the object is turning, if we're thinking of motion. So it points to the concave side of the curve or in the direction that your object is turning. And when we start talking about unit tangent vectors, unit normal vectors, we're starting to get a little bit into, we're just going to touch on what's called differential geometry, where we use calculus to analyze properties of curves and surfaces. So it's kind of a nice, we're going just a little bit into differential geometry, and then at the end of the semester we'll do a little bit more that has to do with differential geometry. We're kind of stepping briefly into a very vast field of kind of a whole new field of calculus and geometry, all combined. All right, so any questions on our tangent vector and our normal vector and how we come up with them? Okay, let's look at an example of calculating a unit normal vector, and then we'll talk about a shortcut that we can use sometimes. So, and before I do the example, just looking at this definition, what do you, looking at this, does this look like it's going to be easy to do or not easy to do in general? Not easy because we have first we have to take the derivative of r to get our unit tangent vector. We have to divide that by the magnitude of r. Hard, lengthy, it can be very algebraically intense. So let's put it that way. So we try to come up with some shortcuts. So let's look at an example. Anytime we have a magnitude and we're taking a derivative and we're taking a magnitude and we have to divide that, then you can end up with some messy expressions. Have we used that word very much recently? Messy? Not since the end of the first semester, have we?
If you're aware of the name, you finish your lecture.
Yeah. Last year they said the word that I used often was straightforward, and they thought I didn't know what that meant. All right. All right, so we want to find our unit normal vector at t equals 2 for this curve. We'll do a nice easy curve, ti plus 1/2 t squared j. And we're just in the plane here. So to find our unit normal vector, we have to find our unit tangent vector and then take the derivative and then normalize that. So to find our unit tangent vector, we need our derivative, r prime. Our prime of t is I plus tj. The length of r prime is the square root of 1 plus t squared. So our unit tangent vector, t equals 1 over the square root of 1 plus t squared times I plus tj. So now we have to take the derivative of this and then find the magnitude of that derivative to find our unit normal vector. So this is why because we have this radical in the denominator, that's why it ends up being kind of algebraically intense. So we need to find t prime to find our normal vector. T prime of t. I'm going to use the product rule. We had a product rule for a scalar times a vector. So I'm going to use a product rule here. So this is the first. I'm going to say the first times the derivative of the second plus the second times the derivative of the first function. The derivative of the first function, I'm going to write it all out here. Minus 1/2, I'm going to write all the pieces. Minus 1/2 times 1 plus t squared to the minus 3/2 times 2t. So there's the derivative of this part. After some algebra, I'm not going to go through all the algebra to simplify this. But once we simplify this, we end up with minus t over 1 plus t squared to the 3/2 I plus 1 over 1 plus t squared to the 3/2 j. So we just simplify and combine our i's and j's here, and this is our t prime. Now, if we wanted the unit normal vector in terms of t, we would have to then divide this by the magnitude of t prime. So that gets really ugly. We want the unit normal vector at time equals 2. So this problem gives us a little break. Now we can just plug in our time equals 2 and calculate our magnitude at time equals 2. We don't need a general expression for the unit normal vector. We just need it at time equals 2. So t prime at 2. I'm just going to plug in 2 here. T prime at 2 is minus 2 over 5 to the 3/2 I plus 1 over 5 to the 3/2 j. So, and now I can find the magnitude of this, the magnitude of t prime at 2. Thankfully, they let us plug in a number. Magnitude is a square root of minus 2 over 5 to the 3/2 squared. Had a hard time writing that 2 there. There we go. Plus 1 over 5 to the 3/2 squared. And when I calculate that all out, it comes out to be 1/5. Not too bad. So my unit normal vector at time equals 2 is 5 times this vector. So I get negative 2 over square root of 5. So I get I'm just going to write 5 times t prime at 2, and then I'll write the simplified version. So I'm just multiplying this by 1/5. I get negative 2 over the square root of 5 I plus 1 over the square root of 5 j. So that would be my unit normal vector at t equals 2. But we could see, once we got to this, how messy it would be to find an expression for n in terms of t. So I have a 5 in the numerator and I have 5 to the 3/2 in the denominator.
You're doing divided by magnitude 1/5.
Right. So
I know that.
so 5 times 5 to the minus 3/2. 5 to the minus 1/2, right?
Then it's 1/5 times t prime.
No, we're dividing by 1/5.
Yeah, so then it wouldn't be 5 times.
Yeah, so we're dividing by 1/5, so it's the same as multiplying by 5.
Yeah, no. So then what I'm saying is it would be 5 times negative 2 divided by 5 to the 3/2.
Yeah, but you can,
Right.
you can cancel the 5 before you multiply by 2.
So for
It's not 5 times 5 to the negative 3/2.
Well, it's the same thing.
yeah, 5 times 5 to the negative 3/2 is the same as 5 divided by 5 to the 3/2, right? Negative exponent, or positive exponent in the denominator is a negative exponent in the numerator.
Oh, yeah.
Okay.
Yeah, sorry,
All right. Are we good?
Yeah, we're good.
It's Friday. All right.
It's a long morning, man.
So in general, finding our unit normal vector can be very difficult algebraically. We'll talk about some other ways to go about it, but in the plane we have a nice shortcut. So here we had a vector in the plane. So in the plane we have a shortcut. Now this doesn't work in space, only in the plane. In the plane, if we have our unit tangent vector is some function x of t I plus y of t j. So we have this unit tangent vector in the plane. We have some function of x and some function of y. We know that because this is a unit vector, we know that the square root of x of t squared plus y of t squared equals 1. because we have a unit tangent vector. We can think of the x of t and the y of t as giving us the slope, kind of, I'm putting that in quotes, the slope of our vector. So what vector would be orthogonal to a vector with these components? What can we do? Right. So they have to be negative reciprocals. So basically what we can do is switch the x and the y and change the sign on one of them. So we're making it so the slopes are negative reciprocals. So we'll say that n is orthogonal, so the slopes are negative reciprocals. So n is either y of t I minus x of t j, or minus y of t I plus x of t j. And you pick by deciding which one points to the concave side of the curve. One's going to point away from the concave side, one's going to point towards the concave side. So you pick n so that it points to the concave side of the curve.
And how do you know which side?
Draw a picture.
No, can you draw, like, can you just draw it?
What it
Like, an
means?
example, yeah.
Which side is pointing to concave?
So if I have a curve here, t is going to be here. We want n to point this direction.
Okay. So just,
So this is going to give us either this curve, or it could give us, or this vector. It would give us one of those two. So we'd want to pick the one that points towards the concave side, not away from the concave side. And now let's look at our last example. Here's our unit tangent vector. We could have plugged in t equals 2, switch the x's and the y's, and change the sign on one of them to get this. So I could have plugged in time equals 2.
do you do it first? Like, does it matter if you plug in 2 first and then switch them?
No.
Or switch them?
Did you do it for t or t prime?
T prime.
I think you're t. Right, not. No, no, that's
On the other page. Yeah, we need n orthogonal to t, right? So we just switch the x's and y's on the t. So right. So I go back here. Oh, this one, yes, t. So if I went here, switch the x's and the y's, and change the sign on one,
Okay, there you go.
then I would have ended up with this.
The two of them are fun.
Right. So we're looking at t. So if I plugged in t equals 2 here, switch the sign on one of them, switch the order, then I get to this. So that would be our shortcut in the plane. But if the problem asks you to find,
Is this shortcut in space?
no, in space there's not a shortcut, unfortunately. All right. Any questions? Homework.